Hello, oh man, and welcome back. So in the last video, we were talking about this idea of hypothesis testing and how we use essentially p-values to make conclusions, essentially. Okay, so we're again working with a small sample, and based on the stuff that we saw in our small sample, we're able to relate it, we're able to infer about the population. Okay. And in this case, we can make two claims based on the p-values, whatever p-value we get. If our p-value is greater than something, some value here, in this case 0.05, which it usually is, then we make the claim that there is no difference between, in our case, the control group and the experimental fertilizer group. However, if our p-value is small enough, meaning that the two samples that we have are different enough, then we are able to say that there is at least some difference. Okay, and we'll get to how we can kind of quantify this difference to the population. Okay, and we use we use t-tests to do that. And the nice thing about t-tests is that we have one for pretty much every situation we can find ourselves in. Okay, the most basic of which being the one sample t-test, where we test the mean of a single group against some known value. Okay, and let's just kind of remember that we use these statistics here, the mean in this case, to summarize a whole sample. Okay, so this mean here, some value that we already know, is representative of some sample. Okay, we just don't have that sample available to us. Okay, but we do have the sample, or our single sample. We have the mean of our single sample. Okay, now you can kind of think of this in a few different ways. Sometimes the known mean, the known thing, is 0. Because we're calculating differences essentially here. Again, not too big of a deal. I'll get to when this becomes sort of normal, kind of used. But this one sample t-test is simple and it doesn't really show up in practice a whole lot. However, this idea is still important. Okay, and then we have our sort of classical idea of t-test, where we have an independent samples t-test, and that's the t-test we would use in the example that I've been using this whole time, where we have our control group and we have an experimental group, and we want to compare the difference between those two. Well, to do that, we would use an independent samples t-test, or a two-sample t-test, because we have two samples that are both independent. Okay, so they're not so much related to each other, or at least one sample is not dependent on the other sample. And that just compares the means for two groups, or the difference in means. Okay. Then we also have a paired sample t-test, or a paired t-test. And that has a kind of time component. So that's essentially when we compare the mean of two groups, but it's the same people just at different times, or the same plots of land at different times. Okay, and we've kind of seen some examples of this previously when we were looking at the, I guess the controlled burn in one of the labs. If we've gotten to that, if we haven't gotten to it, we will get to it. But essentially, if you want to see how something changes over time, kind of like a pre-intervention and post-intervention, you would use a paired sample t-test because, well, you've got the same people in it at each time point. Okay, so these two tests are similar. These two tests are similar, except this one is accounting for the fact that it's the same people, or the same plots of land, just at two different sets of time. The independent samples t-test, the two sample t-test, does not. Okay, so you have two independent groups there. Again, we are still just comparing the difference in means here. And it's just as simple as that. We're trying to figure out, how similar or how dissimilar these samples are, and if that difference is going to be true in the population. Okay. Again, that's what we're always trying to do. We have a sample and we're trying to infer about the population, how something behaves in the grand scheme of things, not just in our sample. Okay. Now, to use t-tests, though, we have some rules. We have some rules that we have to follow, or some assumptions that we have to meet. Okay, and there's only 3, which is nice. And some of these, are pretty easy to get. Some of them are a little bit harder, but that's okay. That is okay. So the first assumption, the first sort of, let me kind of do this too. Rules. So the first rule that we have to have is that the variables must be numeric. Okay, they must be numeric. Some people require that they be continuous. In our case, we can be okay with these discrete values. But what I mean by continuous, or let me just say numeric for now, is that we're comparing two numeric things. So in this case, the difference between height against men and women, same thing with weight against men and women, IQ score maybe against, I don't know, whatever, some different education levels or something. Distance between two things, whatever. These are all examples of numeric values that we're comparing, okay? So we always have one kind of measure across two different groups, okay? And in the case that I just gave here, it's by sex, okay? So the difference between men and women, for instance, or maybe the difference between, I don't know, PhD degrees and MD degrees, maybe just something like that. The difference in doctorate degrees. So we're comparing this one thing across two different groups. And that's the whole idea with t-tests. The next thing is that observations are independent, okay, of one another. Okay, so this is pretty much always assumed. It's representative. That means that you have two samples if you're doing this one. If you're doing an independent samples t-test, then this is something you need to make sure that you got. In this class, you'll always be given data that is independent, so you don't need to worry about it in the sense of a two sample kind of case. But in the case of paired t-test, it's a little different. We don't have to have that assumption because they are totally dependent because you have the same people pre and post something. Okay. So again, this is kind of always assumed unless I give you some kind of trick question. I'm never going to do that, but good to know in practice, right? Okay. Excuse me. And then the last rule that we have to meet is that the dependent variable, or the thing that we are measuring, so height or weight or IQ score or whatever, is approximately normally distributed. Now. Here's the deal with this rule, is that if your sample size is big enough, then this is met, okay? So you do not always need to plot a histogram of our two groups and say, okay, and check the normality, the kind of symmetricness of that histogram. You don't have to do that if your sample size is large. What do I mean by large-ish? Oh man, it depends. It depends who you ask. If you ask me, whatever. You can do a t-test with really, really small samples. That's why we have that t distribution, okay? Because it takes into account the fact that we are estimating kind of the deviation of the population with the deviation of the sample. You can use samples as small as 8, even 6, and you can use samples as large as 1,000, 1,000,000, 10,000, whatever. As long as it's large-ish, you're going to be good. So out of all of these rules here, this one is always going to be given to you. You can always assume that this is true. You can always assume, that the things are going to be numeric. I'm not going to give you some weird thing. Also here, actually, by numeric, what I mean, oftentimes we can code categorical things. So like colors or whatever. Gosh, what else? We'll just stick with colors. So like color of houses. We can code blue as 1 and red as 2 and yellow as 3. Okay, but those are not meaningfully numeric. Those, 1 plus 1, blue plus blue, does not mean you get 2 or red in that case. It's totally just convenient. The numbers don't actually mean anything numeric. They're just being coded as such. And that's kind of what I mean here. They must be truly numeric. Okay, and you can kind of assume that I'll give this to you as well. And then the last one, where they need to be approximately distributed, slash you need to have a large sample size. This is kind of the big one here. Let me just say this. The sample size should be large, okay? And this can look, very subjective. Some people think that 8 is big enough. You just have to be very careful with the conclusions you make. You have to kind of more say that it's an approximation that you're doing rather than a concrete conclusion, okay, with whatever inference you're making back up to the population. Again, these are all good to know. These are all good to check before you do a t-test. But a lot of the time for this class, not so much in practice, but in this class, you can kind of assume that these are good. Okay. Oh man, enough of me talking about 16 slides of what t-tests are and aren't. Let's get into an example. So I'll let you read this in a second. I'm going to pause the video and we'll get into it in R momentarily.